can get going again. We can get started on super insulated walls. Fat walls mean skinny energy bills. So I'm going to go over 4 different configurations for a fat wall, for a highly energy efficient wall. Excuse me. There's a lot of ways to build super insulated walls. Continuously wrapping the outside of a house with some sort of an insulation like foam boards or rock wool is one way. Adding a second layer on the inside so that you can blow tons of insulation adding a second wall on the inside so you can blow tons of insulation into the cavity is another way. That would be double stud walls. Thickening the wall on the outside so you can blow tons of insulation into the cavity would be another way, although less common in the real world. Exterior eye joists. And hyperbolizing a pretty standard system to make everyone pay attention to it is the 4th way, the awesome wall. So these are just 4 ways to go about it. There's a lot of ways to go about it, but I think they illustrate different methods that are pretty different and how they solve different problems that you come up with. The first one is going to be continuous exterior insulation. Sometimes people call this outsolation. I resist that with all my might. I hate that term. Lately, people have been calling it continuous insulation, which I think makes more sense because it is actually continuous. It says what it is, and it doesn't invent a new dumb word to describe it. I still kind of call it exterior insulation because I'm stubborn. As noted in the CI, continuous insulation moniker, continuity is the key. Remembering back from the 7 minutes of BS with Jonathan, that heat is basically a shape-shifting intruder who's going to go out and find the easiest possible way that it can to screw you. And so that's what its job is. If everything else is buttoned up tight, the easiest path for heat is through the studs or other structural members. And remember that thermal bridges accounted for R19 insulation being knocked down to basically R15 with wood stud construction. So that's a 25% loss. 25% loss is a pretty big number. And if you don't think 25% is a lot to throw away, then just please withdraw 25% of your retirement account and send it to me. So here's another early animation that I made right before we launched Pro Tradecraft. It's based on job site guidance from the remodeler who does a lot of work for Joe Stebrick and Building Science Corporation. His name is David Joyce. Not only does David know what to do and why it matters, he knows where the beer is at Joe's house. So here's the animation of a exterior wall and roof retrofit.
Adding exterior insulation to the roof and walls of an old house can improve comfort and energy efficiency. It especially makes sense if the rafter cavities are already insulated, and it's most affordable when the roof and siding need replacement. The first order of business is to strip the roof and walls. Next, cut off the rafter tails so that the connection between the roof and walls can be sealed with peel and stick membrane. Install 2 layers of foam to the roof, staggering the seams and offsetting the joints. Tape the seams on the outer layer. New roof sheathing goes on top, screwed into the framing 1.5 inches. Cover the roof deck with roofing underlayment that will protect against liquid water, but also allow vapor to escape. At the bottom of the wall, a piece of coil stock is bent into a J-channel to keep the bugs out. The metal is tucked behind the house wrap, and 2 layers of insulation go on the walls with the outer layer's seams taped for an air seal. Attach a strip of bug screen to the bottom of the wall to keep the ventilation channels clear. At the corners, weave the foam panels together to disrupt any clear air path between inside and out. Corners are then wrapped with peel and stick to keep them tight. Furring strips are screwed into the foam 1.5 inches into the framing. Box out a soffit at the top of the wall and tie it all together with fascia. Install the siding making sure to detail the bug screen tightly at the bottom of the wall. Continuous insulation and multiple layers of air sealing turn a leaky old house into a 21st century home.
Copyright 2015. So we've been talking about this at Pro Tradecraft for 6 years, but we were talking about it at Fine Home Building for at least another, and Green Building Advisor for at least another 6 years before that. In fact, that's how I met those guys. So it's not new, but it seems new to a lot of people, and now it's actually even in the building code. So let's have a peek at how Dave and his crew do it in the real world. Again, Dave works a lot for Dr. Joe. This is not one of Dr. Joe's projects, but he uses the same details that he learned from the Building Science Corporation. It's a typical split entry ranch that was gutted and retrofitted into a weird modern house. Fun fact is the owner was an engineer, so it's kind of like the worst customer in the world is a retired engineer. So not only is he engineering, but he's got a lot of time on his hands.
Welcome to Concord, Massachusetts. This house is undergoing a deep energy retrofit and gut rehab. To boost the R value, 4 inches of polyisocyanurate foam is being added to the walls and roof. The siding, a sheet product designed to mimic vertical boards, is structurally sound, so it's being left in place and then covered with house wrap and foam. The windows were installed and flashed to the openings before the house wrap, and then the house wrap is sealed to the windows with a flashing tape. Dave explains how flashing tape connects all the layers.
Our flashing membrane from the outside, from the window itself, crossing right over the flange onto the sub-flashing and onto the house wrap. The sub-flashing protects our building from any leak that could happen in the window. The house wrap goes over that and is adhered to that,
which makes a good air seal and water seal. The pan flashing is extended out so that it can drain water to the outside of the foam sheathing. Extra strips of flashing tape can extend the pan flashing more. This is where a split release sheet on the back of the flashing really comes in handy. The 2 layers of foam should have offset seams, so Calvin and Damien begin with a small rip that will fit continuously under the windows. The first course is kept level to keep the measurements consistent, and a metal cap at the bottom protects the foam from insects. It's great to use large pieces whenever possible for a better air barrier, but because there is a layer of house wrap and 2 layers of foam, it's safe to use up some random scraps.
As long as it's not like 30.
And there will be a lot of scraps. As long as the joints are tight and the insulation is continuous, piecing in scraps should be fine. As Dave said earlier, the foam will overlap the window frame to get a tight seal to this opening. In this case, the guys are leaving 2 1/4 inches of frame revealed. Also at the window, they pull the pan flashing out past the foam so that anything that leaks in is drained all the way out. Don't bother to tape the seams on this first layer, because as you compress the foam later, it will just pull the tape away from the seam. The second layer will be taped. As one guy installs, he can measure for the next piece. Working together, 2 installers ought to be able to keep ahead of one cut man. Cutting foam sheets is pretty simple. You can use utility knives with extendable blades to get the whole depth on small cuts, and when cutting sheets in place. Angled cuts are needed where wall foam butts under roof foam. For long cuts, you can use a knife and chalk line, or you can use a table saw.
Yeah, so basically everything that we saw in the animation, but in the real world. Flash the window opening first, install the window, integrate the window with the WRB, making sure that everything seals back to the framing. and then leaving no layers open at the edges. It's a recurring theme we're going to be talking about all day today. Install the first layer of foam, not taping the seams, and using offcuts to fill the pieces whenever you can. In this video, they'll install bigger pieces of foam on the second layer, and then they'll tape the seams and the corners. Again, the foam gets compressed, and if you spend all your time taping the first layer, you're probably not going to get as great a performance. Plus, you're paying someone to spend an awful lot of time taping awful lot of little gaps with a bunch of little pieces. So they'll also install furring strips for siding attachment after they install the foam. That's one sort of method of a rain screen, a vented rain screen wall assembly. There's also a few ways to do that. We'll look at one or two more later on. But let's look at the exterior foam job.
With the first layer of a 2-layer exterior foam retrofit installed, Calvin and Damien turn to the outer layer, which will be the primary drainage plane and air barrier. They begin with a starter piece, again attaching it with 2 screws until the furring strips go on. You may notice that the seams are already taped on these sheets. That's because they wanted to pre-fit the pieces before we shot a video, and then they got carried away and taped the seams. Anyway, the foam is tucked tightly into the bug shield, and they install as close to full sheets as possible. Certainly, they cover seams in the first layer with solid panels in the second. Again, the pieces should be snug. Typically, they work from one corner to the other. In this case, the middle of the house is broken up by a large staircase, so they are working from each corner towards the middle. Once the corner is plumb and level, they fasten it off. Again, succeeding pieces should fit tightly. Cantilever sections, like outside corners, have woven edges, so there is no straight line for air or energy leaks. The bottom of the foam and any exposed edges, such as at a basement knee wall like this, are wrapped in a metal channel that keeps the bugs out. The metal is sealed to the foundation with silicone caulk. Next, the seams and edges are taped with contractor tape. The metal bug shield is taped to the foam also with contractor tape, as are the inside corners and cantilevers. Outside corners are sealed with a wide strip of peel and stick membrane to cover the staggered corner sheets. Next, foam under the windows is sliced at a downward angle to extend the sill pans sloping to the outside. And the peel and stick is peeled and stuck to the foam. Calvin explains the process.
I think it's better to start from the middle, because then you get less wrinkles and stuff, and you work your way outward. Do a little cut, not all the way into the corner, just a little one, so you can get this stuff rolled over a little bit. So that corner's nice and watertight.
Notice that he cuts the corner shy and bends the membrane to keep the bottom point watertight. With the seams, edges, and corners taped, they turn to installing strapping for a rain screen siding assembly. 1x3 utility grade strapping is fine. The second layer of screws are longer, obviously, than the first layer of screws. These are about 6 inches versus 4 inches on the first layer. The screws are countersunk by cutting partial holes in the furring strips with a spade bit. As the furring strips are secured to the framing, the foam is compressed inward. This can make for a wavy wall when it's time to install siding. At that time, the crew will pull a string across the entire wall and either drive in the screws or back them out to get a nice flat plane. That string line process is not worth doing now because the wood framing may still expand or contract before it's time for siding.
Okay, so let's head on over to double stud construction. You can do double stud walls many ways. I've seen photos of people lifting double walls that are like a foot thick. I always wondered how they frame them like that. It's probably not that difficult. And I was expecting to see it happen when I visited a job site in Maine where they were building a double wall house. Ben Bogey was the lead carpenter. But what I saw when I got there is that they just framed the outer walls with 2x4s, stood them, set trusses, got the house dried in, and then came back later and framed inner walls. So it wasn't very exciting to shoot video of, but I was there. It is a heck of a lot faster than framing twice as many walls from the get-go, and it's a half as heavy a wall to lift, so it makes sense. I actually built a double wall structure once back in the 90s. The prevailing advice then in the hippie home building journals was to use like a 2x8 bottom plate and stagger the studs, and then the insulation was woven between them. This is absolutely not the best way to do it at all. You're not going to get good performance of your insulation, your bat insulation, if you're weaving it, and there's no reason to stagger the studs if the bottom plate, or if they're not touching each other. So I even now, when I post videos and animations like this, I get comments that people say that you're supposed to stagger the studs, and the only reason to do that was so that you could use a plate that was smaller than the width of two studs. So like a 2x6 plate with 2x4 staggered, that would be a way to eliminate thermal bridging, but it would be an awful lot of wood for very little R value. So that's not the best way to do it. That's not the way you need to do it. For thick buildings where people actually live in, the double stud structure that I built was a practice space for a rock band, and we were just looking for soundproofing, and it was pretty darn quiet. But for houses that people live in, you usually want a thicker wall than 7 inches, and staggering the studs isn't necessary. So here's how Ben does it.
We learned earlier from Ben and his crew how to frame basic exterior walls using 2x4s. It may have seemed like a low bar on the energy efficiency scale, but that's because the house will have 12-inch thick walls using a double wall approach. With the outer walls framed, sheathed, stood, and capped with a roof, the crew can turn to framing the inside walls.
Tight up to the plate.
Begin with plate stock butted to the outside wall.
And then what I'll do is I'll measure. We're going for 12-inch wall thickness, minus our 3.5 inches for our intersecting plate. So I'll mark my plate cuts there.
Let's take another look at what just happened.
Bottom right, tight up plate.
Not like that. He butts the outside sheathing and marks 12 inches. That's how thick the cavity of the wall is. Next, he subtracts 3.5 inches for the perpendicular wall framing. This is where he will cut the plates off, so the interior walls are not touching the exterior walls.
It's as simple as just coming right across, transferring your layout of your existing.
Copy the wall layout on the inner plates, including windows and doors. Break the ends on studs just like regular wall framing. These hieroglyphics contain a lot of information. The marks begin at the correct line and cross over the line that should be ignored, and also indicate what side of the line is waste. They transfer layout marks from the top and bottom plates to headers and sills, and they fill in the window and door openings. To reduce alignment problems, they frame the interior openings to be slightly larger than the exterior ones. The header on this door is about 1/4 inch higher than the header in the exterior wall. With the window and door openings framed in, it's time to install window bucks to bridge the opening. Ben uses sheets of 3/4 inch subfloor ripped to just under 12 inches. Obviously, the rough openings need to be framed 1.5 inches wider than the window schedule calls for if you're going to buck out the openings with 3/4 inch subflooring on each side. Rather than wrestling large single sheets through a portable table saw, Ben's going to use a track saw to cut 2 sheets at once. So So after flushing up a couple of sheets, he clamps them together with a couple of 8-penny clamps. I can't really see from here what number he's marking, but I bet it's 11 3/4. Combined with the blade thickness of a few cuts and the size of the gap that's engineered into the size of these sheets, he should end with just a whisper of a rip at the end, mostly just cutting the tongue. Align the edge of the track to the marks, plop the saw on the track, and cut. Looks like it was 11 3/4. He cuts the sides, tops, and bottoms to length using blocks strategically placed to either support the stock or let it drop. Inside, he places the bottom buck first, but first he whacks the framing a bit just to remind it who's boss. The bucks are fastened to the framing of the exterior wall only. They're also aligned with the outer edge of the framing, which means the inside edge is inset about a 1/4 inch from the face of the framing.
Yeah, total wall thickness is 12 inches, so I rip them a 1/4 shy because if we have any bow in our wall, I don't want them protruding past and having to come back and either sand them or cut them off. There's nothing critical about the inside edge. It does nothing references off. We'll set the bucks, waterproof them, and then later, after everything kind of has a week or two to acclimate, before we go to set the windows, we'll shim the openings so that we know that they're dead true, square, plumb. It's not super critical, but that's the game plan.
With the bottom and top bucks in place, he slips in the sides. Again, the critical edge on the window bucks is not the inside one, as Ben noted earlier, because nothing references from it. The critical edge is the outer one, snugging up against the wall sheathing. Now, all that's left to do is cut out the sheathing. Rather than blind cutting with a worm drive, Ben uses a router and flush cutting bit. He drills a location hole for the router, pokes the bit through the hole, moves sideways and down, and runs along the bottom buck. Now, he glides the router around the window openings until he gets back to where he started. After cleaning up the edges, he'll be ready to apply some liquid flashing to the window openings. Next time.
So frame the outer walls with 2x4s, makes them easier to lift, and transfer the inside to layout to the inside to the wall plates, and frame the inner walls also with 2x4s, and then make the window and door openings slightly larger than the openings that you framed in the outer walls, which will allow for humpy lumber and just give you a little bit of room for error. There's a variation on this method that I also saw up in Maine at a passive house construction site. The builders were Geologic, Geologic is the name of the company. The outer walls that they were doing were made with SIPs, right? So they stood SIPs walls on the outside, buttoned them up tight, set the roof trusses on top of that, got it all dried in, and then once the house was dried in, then they ran 2x4 interior walls and blew about 9 inches of insulation in there. So it's an even quicker way to get an exterior shell that's pretty tight and complete before the rest of the walls even need to be framed. A little more expensive than double studs, but you know, if you're battling the weather, it might be the way to go. So that brings us to the third method, which is less common, but totally valid. It's a modification of what people call a Larsen truss system. A Larsen truss is basically 2x2s with plywood webbing nailed to the outside of a house to just thicken the wall and make more room for insulation. It's not structural, it's just a place to shove insulation. Ben Bogey is also the carpenter on this project, which was a passive house retrofit on a 1930s cabin, basically. So this is a method you won't find in the building code, but you wouldn't have found exterior insulation in the building code a little while ago either, when we started covering it at Green Building Advisor and Fine Home Building. Exterior foam is in the code now, so builders who paid attention 6 years ago have their systems in place already for meeting those higher R values. The point of the exterior I-joists is not to take up time in the presentation and show crazy stuff that may or may not work, but it's to show a valid solution to the control layers that Dr. Joe defines. Again, it is a passive house retrofit, so they're going for really deep energy efficiency. And one way to do that is just with tons and tons of insulation and great air sealing. As crazy as it seems, when you watch it done, it actually goes together pretty quickly, and it delivers a high performance wall with off-the-shelf materials that don't require really any special carpentry skills. One good thing about this system is that the I-joists disrupt the thermal bridge across the floor and ceiling assemblies too, because you can go from mud sill to top plate, whereas the double stud walls that we just looked at can only fit between the subfloor and the ceiling joist. So you still have, that assembly on the floor that we looked at really early with all those gaps and cracks and leaks. Same deal as up in the ceiling joist. It's almost exactly the same assembly. So there's tons of wood butting each other and nailed together and gaps and cracks everywhere. So one cool thing about this is it does bridge that whole thing. It puts it all inside the thermal envelope. It's really, at its essence, it's just a different approach to exterior continuous insulation like foam. In the first approach, the rigid foam was the actual structure that the insulation needed to go from top to bottom. In this approach, the insulation is cellulose, which sucks at being structural, so they use engineered framing lumber to make a structure to hold the insulation like a Larsen truss. So there's a lot of different reasons why you might want to do this. I suspect the main reason that the architect chose this system for this building is that they wanted to reduce greenhouse gas production. That would have been introduced if they added 10 inches of foam to the roof and walls, not to mention where they'd find long enough screws. So this method is fairly simple, even if a little bit different.
Passive House certification is like a badge of honor for designers and builders. It requires extreme airtightness and energy efficiency, and it usually involves very thick walls. It's hard enough with new construction, but retrofitting an old building to Passive House standards is no place for sissies. This cabin will get a modified Larsen truss system, where 12-inch engineered I-joists are fastened to the outside of the walls and roof. Extreme airtightness begins with taping the wall sheathing. Now it's time to thicken the walls and roof. As they work along the wall, Charles repairs nicks in the sheathing tape that occurred during roof construction. Before delivering the I-joists, Tony pre-sinks screws in the flange where the top plate is. The joists sit on a ledger at the bottom and align with the rafters at the top to keep a continuous thermal cavity. To avoid thermal bridging to the inside, the new framing is offset from the existing framing. The wide flanges are screwed into the top plate with 6-inch structural screws. The joist is then adjusted plumb
Bottom's gotta go towards the front of the house.
and screwed into the rim joist. After lunch, they move to the sunny side of the house, where they keep installing I-joists to the outside, skipping over the window openings for now. Cutting the I-joist is done with a couple of saws and a couple of jigs. Notching the bottom is done with a 7¼ inch circular saw, adjusting the blade depth to the flange width. The length of the I-joist is pulled from that notch to the top point of the roof angle. The cutting jig is made with a couple pieces of plywood and a 1x fence. The lower piece sits between the flanges and the upper piece overlays them. The flanges are scribed and the jig is slid over until the lower piece aligns with the flange marks. The angle is the complementary angle to the roof pitch. After the jig is clamped in place, the upper piece acts as a saw guide while the lower piece indicates the cut line. Filling in under the windows uses up some of the short pieces and requires another jig with a 1/4 inch per foot slope. Here, Tony's making one. He has offset the 2 pieces of plywood the distance from the saw blade to the edge of the saw table, and then he screws them together. A scrap of OSB is used for the fence on this jig. Looks like it works. Now they fill in the window framing, resting the notch on the ledger and screwing the flange into the window framing. Because the existing framing and structure is a bit on the wonky side, they run a string line down the walls at the bottom and top. They check along the wall at each joist for variations, and then they adjust with shimps. This will give a straight wall when it's time to hang siding. Later, the window opening will be boxed out with plywood, which is shimmed plumb, level, and square. But first, we're going to head onto the roof and see how they pull off that piece of the puzzle in the next video.
So, turns out pretty straightforward. Attach a ledger to the bottom, notch the I-joists, offset the existing framing to break the thermal bridge, and screw the joists into the top and bottom plates for a solid connection. So that adds about 11 inches of insulation to the outside of the building, or maybe 35 Rs stuck into the system. And that brings us to the last wall example, but not the last possibility. Here's a wall design that was invented by a local guy to you all, Michael Anschel, OA Design Build in Minneapolis. Michael wanted a wall that would satisfy Dr. Joe's control layers, but still be easy enough to install that people in the field could make mistakes, as they sometimes do, and the wall design would be able to overcome those mistakes. I've worked with Michael for a long time and can tell you he's a great builder. He knows why to do this stuff and why it matters. And we just finished a really cool show called Building Resilience, which you should look for. One thing about Michael is he does tend toward hyperbole, so he calls it the OA awesome wall. And we'll see how awesome it is. The so-called awesome wall uses continuous exterior insulation outside the framing and a closed cell spray foam flash coat between the studs. The spray foam does a good job of stopping airflow in those cavities, and it adds, R13 roughly to the wall assembly. Outside the continuous insulation is a drainage mesh rain screen product that's available. There's a few of them available from different manufacturers. One advantage of the kind of entangled mesh system for rain screens that it has over furring strips is that air can move up, down, and sideways without being restricted by the furring strips. As we saw in the furring strips earlier, the air can't move sideways, it can only move up and down. And so if you butt them to the soffit, air can never escape. So you have to make sure that the air can escape and that it can move around back there. And that happens at the underneath all the windows as well. So not a big deal, but it's a place where people can make a mistake. And that was the point of Michael's wall, is to eliminate as many consequences to people making mistakes, because he doesn't feel like you're ever going to eliminate mistakes. So I wanted to add this video because it puts a lot of the stuff that we've been talking about in the context of a whole house that is actually complete or nearly complete. It also includes some talk about rain screen systems, which I think is important, and pulls siding and windows into the picture. Anyway, the whole package is kind of put in context: the exterior insulation, the rain screen, the spray foam between the studs for the air sealing. He calls it an awesome wall. He's also tends toward hyperbole, as I said. He's also a great builder who is not out to lose money on callbacks and rotten houses. So, you know, I trust the guy quite a bit. This house that we're looking at was basically a flip for Michael. They bought a 100-year-old house, added some square footage, fixed the layout, added a couple of bathrooms, tightened it up, and sold it. And this is somewhere in the middle of the process.
Here we are, you know, just under 2 months into construction, and it's gone from, you know, excavation to framing to turning completely green. You know, we've already got our electricians and our HVAC guys inside. Our plumbers have already been inside. We're just clicking along at a really great pace. One of our goals in this project was to show that you can develop a house in an urban lot that doesn't overshadow the adjacent houses, kind of towering eyesore that makes all the neighbors angry. It's a 412 pitch, and we used the 412 pitch because we wanted to keep the profile of the house low. The only downside to this roof design was that we weren't able to make use of a ridge vent to provide the ventilation for the attic. That meant we had to stick with soffit vents and a few turtles up top, but still fewer than what it was. So when we talked about what makes the OA Awesome Wall so awesome, it's a combination of parts. Our 12 zip system is obviously a core component in that system. But when we add to that is the Benjamin Obadiah home slicker, and that is our ventilated rain screen. It's a multi-directional system. It's not just channels between strapping or battens where it's just going up and down and you have to make sure it has a release point. It goes left, right, diagonal, etc. So if somebody accidentally screws something up, if they didn't leave a wide enough gap at the top where the cladding meets the freeze board, we're not going to end up with a wall that isn't venting properly. You also see a bunch of white furring strips going up. This is another component in the system. That is what's going to hold the solid cellular PVC cladding and trim system so that they stand off from the wall an extra ½ inch or so. This is important because it's a cellular PVC cladding. Cellular PVC moves a fair amount, and so we need to give it space to do that. So those corner boards overlap the siding. The siding runs back behind them, and it gets about an inch gap on either side of the wall. The siding is pinned in the middle, just like a typical vinyl siding install, so that it can move left and move right. The board and battens are pinned in the middle, and they move up and down, except at the deck where they're pinned at the bottom and they only move up. So the real trick with this system is just knowing where to pin the claddings so they can move in the right direction. So solid cellular PVC, this is called Select, and it's from Royal Building Products. Those corners are single-piece corners, so they are already pre-90'd, and they come in very, very long runs if you want them. They make for just a beautiful, clean edge. But more important than that, the entire cladding system has a Kynar 500 finish on it. Think of it like an automotive finish or a metal roof, where you're putting up a product that will last for a very, 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 very long time. It's a lifetime warranty on the product. That Kynar 500 finish has a 25-year warranty against 5% fade, and that's saying a lot. This is another cool component in the system. This is a vinyl window from Sierra Pacific that has an extruded aluminum exterior and a solid wood interior. That's cool because, you know, when we're doing energy efficiency, we look to vinyl windows to be more energy efficient. Unfortunately, aesthetically, they're still ugly. So we have the attributes of a vinyl window, but we get the extruded aluminum on the outside for the durability, which makes the consumer happy. And we have the solid wood interior, which makes the consumer happy, and it's aesthetically beautiful. So it's a win-win in all three layers of the window. The other thing about this window that I like is it doesn't have fold-out flanges. So when you're installing it, it's a solid vinyl frame. Makes it much easier to square up in the opening, much easier to install. Like everything else that we did in the system, we were trying to come up with multiple redundancies because the reality of our industry is that things get screwed up, and we have to assume that 5 to 10% of any, whatever gets put together will get put together a little bit wrong. In this case, you could put it together 40% wrong, and we would still have a ventilated rain screen. And that is, to me, is key in making sure that wall actually is able to resist any rot, moisture accumulation over the next 100 to 200 years. So we call it the OA Awesome Wall, a 200-year wall, because making that wall fail at this point becomes incredibly hard, even with people making mistakes along the way.
Okay, so that's basically the end of the superinsulated wall section. 4 approaches to wall systems, 4 very different approaches to wall systems that stop water, air, and heat. They all do it differently, but they're all effective. They all have some challenges and they all have some benefits. And as always, it depends on the house, the crew, and the materials at hand that are available and that your crew is used to working with. There are a lot more videos about this type of stuff on Pro Tradecraft, and additional information in places that I keep sending you to: Building America Solutions Center, Building Science Corporation, Green Building Advisor. Feels funny for me to send people to what's technically my competition at Green Building Advisor, but I was one of the founding editors there and I trust the heck out of those guys. And so I want them to succeed. I also put Passive House Institute US at the top of this list because they have a really great builder training program. It's pretty intensive and it's not for sissies, but it's fantastic. You'll learn a lot more about what we're talking about today. They're all passionate about solving climate change with better buildings, and they're founded by builders, architects, and engineers, so they're a great resource of information. They have a pretty killer conference as well. There's also a section on Pro Tradecraft, which we will email out to you after the session, and we'll have a link to all of the information in this presentation. And once again, we're at that time where it would be good for you to ask questions that I'm capable of answering.